All righty. This video is going to be about how you can, with 2 points in an asymptote graph, write the equations of logs and exponents in 10 seconds or less. All right, and there's an infinite number of ways of writing these curves, but I'm just going to do some minimal work. 2 points in an asymptote, and over here, 2 points in an asymptote. All right, writing these equations mechanically under 10 seconds. Okay, there aren't too many functions that, if we have the right data in front of us, we cannot write in more than 10 seconds. It's just gotta look at the tricks of the trade. All right, so this is based on understanding b to the 0 is 1. This is for, I guess, if we're just starting out here, I probably would need to make sure that students know how to evaluate 4 to the minus 3/2 and how to write it in logarithmic form. But the gist of this video is just going to be about the graphing aspects and writing those equations. So let's have at it. So y equals, well, we got a y, that's the most important y, which is 10. Then we ask the question, how do you get to 17? Looks like you got to go up 7. And how do you get from 10 to 24? Looks like you got to go up 14, not 7. And then we want to make a 0 out of the number 5. So we write x minus 5. And then we look at how far it takes, how much it takes to change from 5 to 25. That's 20. That gives us b to the 1, which is b. All right, so we drop a 5 in. 2 to the 0 is 1. 1 times 7 is 7, plus 10 is 17. So we're nailing that one. And we drop 25 in. 25 minus 5 is 20 divided by 20, which is 1. 14 over 7 to the 1 is 2. 2 times 7 is 14. So we get that jump and we get that jump. And 14 plus 10 is 24. It's that quick and that simple. Now, this was, wants you to see growth. Yep, there's your exponential growth. Okay, when you switch the x's and the y's, I don't want to get this marker all over me, so I'll put it down for a second. When you switch the x's and the y's, you're going to get a graph that looks like that. So instead of those vertical differentials, you really have horizontal differentials. Okay, but to write the log, put the cap on here so I don't lose the cap. All right, I think we can see everything. I guess it's got to go there. It's not on very tight. All right, I'm going to leave that here. Don't forget where you put it, Jim. All right, so, this is really an exponential in that direction. So x is equals ab to the y plus c, but we're going to write it with y equals. All right, and if I'm writing y equals, I might as well start with a y value. Why don't we start with 5 and ask ourselves, how do you get to 25? Got to go up 20. It's a logarithm. We've got to explain that in another video. And so asymptote based on the number 10. So x minus 10. I got to have numbers bigger than 10 or this is not going to exist. This graph's not going to exist. We need positive amounts in that parentheses because over here, we're going from time to amount. Over here, we're going from amount back to time. You don't have anything doubling or cutting in half unless you got a positive amount of something. Okay, so these have to be positive values. So I drop a 17 in, that's a change of 7. Well, that's actually this differential. And then this one is 14 from 10 to 24. From 10 to 24 is 50 is 14. Okay. And so I drop in the 24 minus 10, 14 over 7 gives me a base 2, which is really what this was, right? Base 2. So that's the inverse. Doesn't take long to write. Yeah, it's going to take a while conceptually to grasp what's going on. But that's just the mechanics. All right. And if I wanted to get the inverse from a textbook, then I would do so by looking at this, switching the x's and the y's. Can you still see this? So that becomes an x, this becomes a y. And I should get the same equation when I solve for y. So let's write y equals. Let's write y equals. All right, and here's my first x. What am I going to do? I'm going to subtract 10. Boom. I'm going to divide by 7. Boom. The inverse of 2 to the is log base 2 of. So that's a log base 2 problem. Boom. I'm going to multiply by 20. I'll put a little dot there for you. And then I'm going to add 5. That's what I had a second ago. right? But I don't need to solve that for the inverse. I can build the inverse off of what I see here. Right, so that's the first practice problem. Okay, you pause the video and see if you remember any aspect of what I did. Because it does take practice. That's where this is different from a typical language. Sometimes, in order to learn the language, repetition is your friend. But not only do you have to, get the reps in, but you have to kind of say, hey, what's going on here? And that's where you have to assume the pause, the position. Where you just might have to look at something. Yeah, might have to think. Okay, but the mechanics you can learn quickly and easily. Okay, so let's look at writing this from scratch. I was playing around with this one a little bit before. All right, so we got our differentials from 8 to 12 and from 8 to 20, 12 to 4. Looks like we got a little tripling taking place. Every what? 1950 to 2023, 73 years. All right, so y equals 8. Everything is where above 8 on the graph? Above it. It's a good sign right there. Plus, how much? 4 the first time. The next time, not 4. The next time, 12. There's our tripling differentials. I'm going to make a 0 out of 1950, x minus 1950, and every 73 years. There we have it. The inverse of this should be x minus 8 divided by 4. Yeah, you can see that. Log base 3. Gets rid of that. Multiply by 73. And add 1950. And so here we're going from amounts back to time. And that's our y, right? So we're starting with amounts going back to time. Here we're talking about time to amount. Okay, so they're inverses. But let's do it based on the data. Okay, so what do I see? I see 1950 as my first y. Oh, I'm going to 2023. That's 73 years into the future. I'm building a logarithm off of the asymptote of 8. X minus 8. And I'm using my first x value here. First x is 12. And so I drop 12 in, and that's a difference of 4. But this is based on log base b of 1, which is 0. Right? 0 is the easiest number to multiply anything by. So this whole class is based on zeros and ones, using them and making them. All right, how much fun we can have with that. Graphing these things quickly. Where was I? No, I got to get the base. Okay, so the base comes from our second x, dropping it in. 12 minus 8, 20 minus 8 is 12 divided by 4. There's your base 3. And you can see it's the inverse of this. Can you see that? All right, that's what we had here, I believe. Yep, addition of 1950. Yep, multiplication by 73. So there's different ways to get that equation. But we're learning how to take a graph, which in this case is an asymptote of 8. We're building the graph. That's the inverse of growth. That's, remember what we had here. Yep, that's your growth function. That's decay, sorry. That's your growth function, right? Switching the x's and the y's, getting us this graph where I can see what makes a 1 here, 12. What makes this 3? 3 times 4, 12 plus 8, 20. Right, so that's really a change of 4 and a change of 12 from a graphical standpoint. And then if you drop in a 12, this becomes a 1. Log base b of 1 is 0. 0 times anything is 0. That gets us our 1950. And dropping in a 20, I guess I got to get back to x. I'm not going to do it again. But 20 gets you 73, 2023. All right, and I lost track of where I was there. All right, so that's your second practice. Let's do Newton's law of cooling. Oh, I got to bring my growth and decay piece of paper here. Newton's law of cooling, exponential decay. It's a little harder to see why the graph looks like this, but I'll always switch the x's and the y's for you. I'm looking at growth there. I'm looking at decay this way, so that's what you should be looking at. Okay, and that's this function. When I switch the x's and the y's, I get that function. That's what it is. All right, now And I lost my cap. I'll get that later. Can we see? Let's go back a little bit further with my trusty science card. All right, that way I think we can see everything. Yep. All right, so here we have Newton's law of cooling. I got my coffee here. All right, 60-degree room temperature, new building here. State of the art, 60 degrees forever, unless the thermostat changes. It's that good. All right, but my coffee, 140 degrees. I have no idea what hot coffee is, the temperature. But I'm calling it 140 so that the numbers are user-friendly. And I'll change this so the numbers aren't user-friendly in a moment. But right now, user-friendly numbers. And I don't think we need that third one right now. All right. You can go back and pause it and see what's going on there. All right, so how do we do this? By erasing first. 5, 16, 27. Hope you see 11 minutes lapsing on that timeline. But we're going to write y equals. What's the most important y value? Maybe you know from the previous two we did. That means you're learning. We're measuring things from 60 degrees. I'm going to put the units of measurement in here this time. Okay, so that you can see the conversion in terms of units. So I went from 60 degrees to 140. That's up 80 degrees. The next time, my next reading is not up 80 degrees. I'm going to cancel that out for my second x value when I drop 16 in. I'm going from 60 to 100. That's a 40 degree. Okay, well, degrees cancel here. Degrees divided by degrees cancel. So I'm getting a shift now from time to degrees. Right? And what time is important here? 5. Maybe I should put a t here. Now I'll put an x. X minutes minus 5 minutes. Divided by the change in time. 5 to 16 is 11 minutes. Okay, so that's it. Now what happens when I put 5 minutes in here? 5 minutes minus 5 minutes is 0. You divide anything into 0, you get 0. So I get the number 0. Right, so let's actually put a 0 here. 40 divided by 8 is just a half. Well, 1/2 to the 0 is 1. I get a jump to 80 plus 60, which is 140. Let's go back. Let's do x minus 5 without writing minutes this time. And let's drop 16 in. 16 minus 5 is 11. Let's divide by 11. So 16 minus 5 is 11 minutes. That's still minutes, change in minutes. Divided by 11 minutes. Well, there we go. Just got a generic number now, 1. 1/2 to the 1 is a half. A half of 80 degrees is 40 degrees plus 60 degrees, 100 degrees. So the units cancel or convert, and the numbers work nicely. Okay, so x minus 5 over 11. Now it's quicker to write it from the graph than it is to find the inverse, but let's do the inverse anyway. Change the y to an x. Let's subtract 60. And let's divide by 80. And I'm putting the degree symbols in there. Let's take log base 1/2. The inverse of 1/2 to the something is log base 1/2 of something. Let's multiply by 11. I'll put a little dot there for you. And let's add 5. That's what we're going to get for our inverse function. Okay. Now, it might be a little different when I write this. This is a little awkward because you need to know some rules about, back to what I mentioned earlier, 4 to the minus 3/2. You have to know what that minus sign does exponentially. And I'm sure I'm going to have to spend time on that in the first couple of days of classes. But right now, it's just the mechanics of this. All right, so here we have degrees are our x-axis and time is the y. Right, so 140 degrees came from the 5 minute, 100 degrees came from the 16, right? And the y values are going down. Feels a little dyslexic when you first start doing this. Okay, so let's look at this without that there, and let's build this off of those two values, because that's what we built this one off of. So we'll talk about that later, perhaps, maybe not. All right, but what is the equation here? Well, you're starting with y equals. Let's start with the one you see, 16. Right, and how do you get from 16 to 5? You actually go down 11. This is a logarithm. I'll use that L. Right, and the logarithm is based on the x values. And the first x value I see is 100. So I'm going to write x minus 100. No, I'm sorry. First is 60. That's the most important one. We're measuring from 60. Almost butchered this. Right, I'm not starting again. So x minus 60. Sometimes when I'm chatting, doesn't go well anymore. Okay, so I drop in 100. 100 minus 60 is 40. I'll put the degree symbol there. And then the next one, I drop in is 140. 140 is 80 over 40. 80 degrees over 40 degrees. Right, and that's a double. But remember, there's a subtraction here. So 80 degrees divided by 40 degrees is 2. Okay, but a logarithm is an exponent. All right, if I take the exponent 5 and I do it to the 1, I get 5. But if I do 5 to the negative 1, I get 1/5. So subtracting is the same thing as adding a flip. All right, and that is the equation that you were looking at. Okay, so that's a little awkward at this stage, right? But the actual writing of it still follows the same process. There's differentials here. The first differential that we see is a differential of 60 to 100, which is 40. The next one is this, I guess that's the asymptote here. 60 to 140 is 80. Okay, and so we can see kind of a doubling effect, but we're subtracting, so flips the base. Okay, all right, then. The video is there, and there's other practices, logarithmic and exponential graphing already. I'll try to find those and just call it library series graphing exponentials and logs practice 2 or something. I'll go look for it. All right, but that gets the seed planted. It gets us started early in the semester, which means we can start talking about these things for the entire semester.